Hi, I'm Tyler, and I'm a software engineer at Facebook's Boston office, working on the Conveyor team, where I'm excited to be building out the next generation of continuous deployment tools at Facebook. As you can probably guess, our company runs a lot of code. We have the Facebook.com web servers, we've got mobile apps like Messenger, WhatsApp, and Instagram, we've got backend microservices, databases, machine learning models, and most of these applications are updated through a single system known as Conveyor. Conveyor is Facebook's continuous deployment system, which operates 100,000 deployments each week across the Facebook fleet consisting of millions of machines, all while achieving a 99.9% success rate. But this certainly wasn't always possible. And in today's talk, I'm excited to share with you the evolution of Conveyor and how it evolved from a simple Python tool to a robust system comprised of Rust microservices capable of operating at Facebook scale. But before I can do that, we need to take a trip back in time. The year is 2014, and you're the technical lead of a small backend team at Facebook. How do you deploy your code? Well, there is one tool available called fbdeploy, which is capable of SSHing into your team's hosts and installing a newer version of your binary. But this by itself isn't enough to make sure your deployments are safe and regular. So you take some time and invest in some custom tooling that leverages fbdeploy. Because you have awesome engineers at your disposal, this custom tooling works pretty well. But if it breaks, you're on the hook and your team is responsible for fixing it. Now, this might work okay for some teams, but one engineer grew particularly frustrated when he joined Facebook and spent several months building out a deployment pipeline and then changed teams and had to do it all over again. So he decided to build a better, more generic command line tool that could be used by all teams at Facebook. This resulted in a tool called Push, which was a service registry and command line tool written in Python that could deploy containerized services. As you can guess, Push had a long road ahead of it, and I'm going to break this road into a couple smaller chapters. The first chapter begins in 2014 when a team of engineers set out to make Push better than fbdeploy. And this meant two things. First, Push needed a way to deploy services in smaller incremental phases. And secondly, it needed a way to ensure that each deployment was safe, meaning the new version of code doesn't introduce any bugs. At first glance, this seems easy, but in 2014, Facebook was not a small company. It had IPO'd 2 years ago, and the teams within it were extremely diverse. So making these features work with all teams was actually a pretty big challenge. And so most services are actually replicated across many clusters running in data centers all across the world. And when we update all these replicas, we shouldn't do it all at once. Rather, we should do it gradually in smaller phases to minimize the damage of bugs. And you might think I'm still not understanding why this is so hard. But not all teams actually want the same thing. High criticality services might want to be deployed or should be deployed in many smaller phases to make sure that the service is healthy, whereas other services should be updated in a couple larger phases, which minimizes the amount of time between landing code and getting that code deployed in production. And it would be really great if the Push command line tool would let users express this. And so to do this, the Push command line tool allows users to register their service with a push plan. Now, a push plan is an intent-based execution plan for your deployment, exported via a Python push plan config. Now, this push plan config consists of various phases, where each phase consists of a target, an update amount, and an amount of time to wait before proceeding to the next phase. In this case, we have a push plan consisting of 3 phases. In the first phase, we update 5% of hosts in the Prineville data center region. In the second phase, we update 25% of hosts in the Prineville data center region. And in the last phase, we update all hosts in all regions. And the amount of time that we should wait after each phase is 20 minutes, and then an hour. So this makes deployments or incremental deployments extremely flexible and easy to set up. But it's really only half of the battle. We need to make sure that we catch regressions as they happen. How do we do that? Well, we know that our service has metrics associated with it, such as memory, network utilization, crashes, number of failed requests. And when a highly qualified service owner deploys a new version of their code, they rely on visualizations of these metrics to understand a story of what's going on their service. For example, if we observe a spike in CPU during a deployment, we might think that there's a bug in our new version of code, for example, an infinite loop. But if our highly qualified service owner observes a spike on all hosts, both the hosts running the old version of code and the host running the new version of code, he or she knows that this spike in CPU probably isn't due to a bug in the new version of code, but rather a load spike putting some additional load on our system. On the other hand, if only one host is running the new version of code, and that's the only host that observes the spike, well, this is a different story. We can be reasonably confident that the new version of code is responsible for the spike in CPU. So it would be really nice if push could be smart enough to do exactly what our highly qualified service owner is doing, that is, piecing together certain metrics, comparing them against either an absolute or relative threshold, and deciding whether or not the service is healthy and any ongoing deployments should be aborted or should continue. And so to allow users to do this, they can set up a health check config and use that with their service. Now, each health check config exports various checks, and each check consists of a metric, which is read from some data store, a transform that we can apply to that data to maybe smooth it out, and either an absolute or a comparative threshold. In this case, our service is healthy if the number of crashes in the past 30 minutes does not go beyond 3, and it's healthy if the CPU utilization of the host running the new version of code does not exceed more than 50% more than the host running the old version of code. So if we take a second to zoom out, push is essentially a feedback loop. It issues updates to containers. Those containers report metrics to a health check service, and that health check service reports a signal back to push. This is great. It means we can deploy our service incrementally and safely. But despite the best efforts of the team, in 2017, the team maintaining push found that only 12% of services were regularly being deployed. And this means that some teams might not be using the push command line tool at all, while others might be using it on an ad hoc basis, say once or twice a month. And this led to some problems at Facebook. The first big problem was that critical patches couldn't be shipped quickly enough. So imagine that a security vulnerability is found in a low-level library and a fix is landed. Well, even if that fix is landed the next day, there's no way to guarantee that it gets shipped to the entire fleet if services aren't being regularly updated. The second problem is that if services aren't being pushed often enough, each deployment introduces many changes. And if a deployment breaks everything, it's hard to identify which change is actually responsible for the breakage. So by 2017, the goals of the team had shifted. Rather than building out new features, it would redirect its efforts towards increasing adoption at Facebook. And so a question was raised. Why aren't services deploying regularly? Well, after some investigation, 3 main reasons were identified. First, the push command line tool lacked automated scheduling. You had to remember to run it. Also, there was no support for some services at Facebook that didn't run inside of containers. And lastly, nobody was actively encouraging teams to switch over to Conveyor. So how did we address these problems? Well, first, the team created a new flagship product called Conveyor. This product wasn't a replacement for the push command line tool, but rather it was a more generic deployment system that allowed users to build regularly scheduled deployment pipelines. Now, each Conveyor pipeline consists of various nodes, which can be thought of as stations along an industrial conveyor belt. Now, Conveyor pipelines typically start with a build node, which plugs into a CI system, and might include various test nodes that ensure that the code is bug-free and performant. And most pipelines end with a push node, which is more or less the same as running the push command line tool manually. But unlike the push command line tool, this is a completely automated system. But unfortunately, not every team could use Conveyor on day one. This is because the push node was built from the push command line tool, which only worked for Twine-based services. Twine is Facebook's container platform, which is used by most, but not all, backend teams. Some teams might run their code on bare metal hosts and update them directly through SSH. Other teams own widely deployed binaries, which are bits of code that run on most or all machines at Facebook. And updating all of these hosts one by one wouldn't be very scalable. So instead, machines run a configuration tool called Chef at regular intervals, and this configuration tool is capable of installing all of the necessary widely deployed binaries. Ideally, push would allow all teams, no matter what type of service they own, to deploy their code through our system. And so to do this, the conveyor team modified push to be more generic. We introduced a notion of push types, which are libraries that would integrate with the push system, either through the command line or through conveyor. Users could configure their service to deploy with a conveyor-owned push type, like twine push type or widely deployed binary push type, or they could go ahead and write their own and use that. This allowed teams to move on to conveyor with minimal setup and let them take advantage of health checks, incremental rollout, and automated scheduling through conveyor. But most importantly, the notion of push types meant that no team had an excuse to not use conveyor. It was just a matter of encouraging them to switch over to conveyor. But encouraging adoption wasn't something the team could do by itself. Instead, a company-wide effort known as Push for Push was started, and at its essence, Push for Push did three things. It tracked the percentage of automated services at Facebook. It created easy onboarding tools that would help teams switch over to conveyor and push. And it created staleness alerts for teams that weren't updating their services regularly. So imagine you're a service owner and you're not actively updating your service. You keep getting these staleness alerts and you know that onboarding to conveyor is only a few clicks away. This makes transitioning to conveyor pretty much a no-brainer. And so in less than 2 years, 94% of services were deploying regularly using conveyor and push. This is a huge win for us, and as you can imagine, the number made the team pretty happy. But as much as we'd like to call it a day and go home, there was another big problem on the horizon, and it had to do with the evolution of our system over the years. Now specifically, some of our initial design choices, which made sense at the time, presented scaling challenges as our team and our system matured. Python, for example, worked great when push was a command line tool, but it resulted in frequent typing bugs as our system scaled. Our codebase was also a monolith, consisting of a push service and multiple push types, which was easy to monitor and test at first, but resulted in leaky abstractions and spaghetti code later on. Lastly, supporting both a command line tool and a remote deployment tool made it easy to shift from a more manual deployment mode to a more automated one, but resulted in a lot of duplication in our code base and made it pretty difficult to make sure that every feature would both work on the push command line and through conveyor push. So at its worst, 1 in 20 deployments were failing. This doesn't count health check failures or failures due to misconfigured setups, but rather just bugs, failing dependencies, and race conditions. So how bad is this? Well, if we take the number or the percentage of pushes that are failing, and we multiply that by the number of pushes that are happening each week, and we multiply that by the developer time spent per failure, this amounts to some pretty significant costs for the company as a whole. So it was clear that something needed to change. And so in 2019, with our adoption goals met, the conveyor team shifted towards reliability. And to achieve this, we rewrote our push system from the ground up, learning from our previous mistakes. This new system would be called Push v2, and it would feature a new architecture, new user interface, and new user-facing configs. It would also improve upon its predecessor in a few ways. Namely, it would use a language with better compile time guarantees. It would use an architecture consisting of smaller, isolated components with clear APIs. And it would conduct all pushes remotely. So instead of using Python or C++, we chose Rust as our language of choice because of its strong compile time guarantees, its speed, and the fact that our developers love using it. There were some downsides associated with Rust, however. Some libraries, for example, like Facebook's ORM layer, didn't work in Rust on day one. So instead, we needed to invest some time to port this library from C++, but then it was mostly smooth sailing. Next, our system needed to be easy to monitor and reason about, so we split it up. Now, without going too much in detail, the original push code base consisted of an integration with conveyor, an execution layer, and various push type libraries, as well as an integration with our command line tool. But in our new system, we would have a front-end service capable of handling the details of starting and stopping pushes, an execution layer for handling the end-to-end lifecycle of each push, and multiple independent push type microservices capable of handling the smaller details of like sending updates and running health checks on each type of service at Facebook. We also offered a new command line tool, but rather than conducting a push locally, it would delegate the deployment to the front end. We also designed our system to better reflect Facebook's deployment patterns. And what I mean by that is pushes don't really happen uniformly. Rather, load is extremely spiky and concentrated around noon West Coast time, which is when most teams want to deploy new versions of their code. So to ensure that our system isn't overwhelmed during these load spikes, we split up our execution layer into smaller components where each component is separated or protected by a queue. These components included a orchestrator, which makes the high-level decisions about the push, a worker to process the push plan config, a worker to send updates, and a worker to run health checks. Now, each of these queues before each component can backfill with requests during load spikes, guaranteeing that resources like CPU and memory don't get depleted. So at this point, our story has nearly caught up to modern day. It's 2021, and the new system is mostly complete, and it's time to move users over from the old system. But as with each chapter preceding it, this chapter presented a couple challenges. For example, the new system used new user-facing configs, which needed to be built from their older counterparts. It also didn't support all services on day one, so we needed to keep track of which services were and were not eligible to be on the new system. We also needed to shift traffic to the new system gradually as to not overwhelm it on day one. So we asked ourselves, what's the best way to go about this? Well, all three of these problems were addressed by building a translation layer, which at the start of a push would generate new user-facing configs, check for any exclusion criteria, and check the state of the migration rollout. This is a much better approach than manually migrating users because it's less work, and if we realize that one class of services doesn't work, we can add a temporary exclusion criteria for that class of services, fix any underlying issues, and then roll them back onto the new system later. So this is really great, and it allowed us to move traffic over to our new system and fix bugs before many users were affected. But how did we actually go and find those bugs? Well, we introduced a mechanism to classify each terminal push into one of three categories. A push can be a success, meaning all updates were sent and the service is healthy. It can also be a good failure, meaning the deployment failed, but for a good reason, like there was a bug and a health check failure resulted in the push being rolled back. Or the push can be a bad failure, meaning the deployment failed due to a bug or a failing dependency on our end. And so we split up all of these bad failures by reason and added dashboards to help visualize them during the migration. Then, over the past few months, we gradually shifted traffic onto our new system while closely monitoring and fixing the top causes of bad failures. In early June, we hit our H2 goal of having 95% of our traffic on the new system. And as this chapter draws to a close, we really have to ask ourselves, were we successful in making our system more reliable? Well, to recap, back in 2018, before the rewrite, more than 1 in 20 pushes would result in a bad failure. Now, with our new system, fewer than 1 in 1,000 pushes results in a bad failure. And this number is actually outdated. It's closer to 1 in 3,000 now. So yes, we can confidently say that our efforts were successful and our system is much more reliable. But the journey isn't over yet. In addition to improving our system and adding new features, there are a couple big projects on our horizon. For example, it would be really nice to add latency tracking, which would allow us to catch bugs that don't necessarily result in pushes failing, but might make pushes take longer than they should. We should also have better tolerance for disasters when a data center goes down due to a power outage or a natural disaster. And lastly, we need to finish our migration to the new system, which means moving over the remaining 5% of traffic. So that concludes our journey. I'd like to thank the Conveyor team for all their hard work over the years, and I'd like to thank you all for listening. I hope you enjoyed it.